Alright, this is Mr. Gillum, and today we're going to learn about how to see if a quadrilateral is actually a parallelogram. So there's a few tests we can run, a few things we can check for just to see. And basically what we're going to do is we're going to look at the converse of a lot of these things. Okay? By definition, a parallelogram has two sets of parallel sides. This we know. Alright, but there's also other ways to tell if it's a parallelogram, meaning that the lines are parallel or the quadrilateral has two pairs of parallel sides. Okay, one of the ways is the converse of a theorem we already know, and the theorem says if it's a parallelogram, then opposite sides are congruent. Well, this says if opposite sides are congruent, then the quadrilateral is a parallelogram. Okay, so it guarantees that if opposite sides are congruent, then it is a parallelogram. So there's one way, so it's just the converse of what we already know. Another one says if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So once again, this is something we already know. If this was a parallelogram, we would know the opposite angles are congruent. Now we know the converse of that. If the opposite angles are congruent, then for sure it is a parallelogram. Okay, so another converse, something that is the same thing, just said the other way around. All right, we also know about diagonals. If the diagonals of quadrilateral bisect each other, then it is a parallelogram. So we knew this before. If it was a parallelogram, then its diagonals would bisect each other. Now we're using its converse. If the diagonals bisect each other, then it is a parallelogram. So these are all things that are literally converses of theorems that we already know. Now this theorem, on the other hand, isn't one that isn't a converse of something we already know. It says if you have two sides that are parallel to each other, and then they're indicated to be parallel, like AB and DC, and AB and DC are congruent, then it is a parallelogram. Okay, so if you have opposite sides that are parallel and congruent, then it's a parallelogram. So that one might, you have to remember that one. Determine whether the quadrilateral is a parallelogram. Justify your answer. So right away I know that the first one is a parallelogram because it has opposite sides that are congruent. So this would be a yes. Okay, yes. Opposite sides of the quadrilateral are congruent. Okay, so therefore it is a parallelogram. In this case, it says that justify your answer. So in this case, it says, okay, so we have opposite angles that are congruent, and we have a side that's congruent on each one. Interesting. It doesn't say anything about being parallel. Let's see here. If I extended these lines a little bit, let's just see if there's any relationships that we can use to help us figure this out here. We don't know that they're parallel. We do have a theorem that says if the opposite sides are parallel and congruent, then it is a parallelogram. We also have one that says if the opposite angles are congruent, then they're a parallelogram. But let's see here. Because I don't know if these are parallel lines, I don't think I can prove that it's congruent. So I'm going to say no. I don't think we can prove that one's congruent. I don't see any parallel lines up there to justify having a consecutive interior angles to prove that. And gonna say no. Say no. I'm gonna say no. Okay. Taking a look at the next one. Now we got a little bit more of a challenging problem. It says if fk is 3x minus 1 and kg equals 4y plus 3, jk equals 6y minus 2, and kh equals 2x plus 3, find x and y so the quadrilateral is a parallelogram. So let's see what we're dealing with here. I have a feeling it's going to have to do with something with the properties of diagonals. Fk is 3x minus 1. And make sure that looks like an x. 3x minus 1 and kg is 4y plus 3. And we have jk 6y minus 2. And we have kh is 2x plus 3. All right, so let's use what we know about parallelograms, okay? We want it to be a parallelogram, and one of our theorems says that if the diagonals bisect each other, then it is a parallelogram. So I'm going to shoot for that one, all right? I'm going to say that as long as these are equal and these guys are equal, then I know it's a parallelogram. I can prove it. So I'm going to use x value that's going to make them equal. So I'm going to actually set the parts of the diagonal equal to one another. I'm going to solve for this guy and say x must equal 4. And I'm going to do the same thing here. 6y minus 2 equals 4y plus 3. I know that if their diagonals are bisecting each other, then for sure it is a parallelogram. So that's how I'm justifying what I'm doing here. Finding the value that's going to make that a true statement. And I'm going to say y equals 5/2. We should really write 2.5 since we're talking about measurement. So in this case, if x was 4 and y was 2.5, for sure it would be a parallelogram because the diagonals would bisect one another. Okay. And finally, I think this is going to be a piece of cake for you here. Oh, just a little review slide. So showing that a quadrilateral is a parallelogram, these are your things. So when we do proofs, these are the ways you can do it. You just need to show one of these things. Either show both pairs of opposite sides are parallel, show that both pairs of opposite sides are congruent, show that both pairs of opposite angles are congruent, so both pairs. So that goes back to that one I was looking at. I was trying to figure out if that was, nope, that's a no-go. So show the diagonals bisect each other, that's what we just did, and show a pair of opposite sides are both parallel and congruent. All right, so if any of those 5 things happen, then we know that the quadrilateral is a parallelogram. Finally, I just want to review with you on what slope is. Slope is rise over run. Okay, and you may have learned that when you're graphing lines. It's also known as the rate of change. You might call it the rate of change. We have a quadrilateral here on the coordinate plane with the vertices 2, 3, 8, 4, 7, -2, and 1, -3. And it's already depicted here in the diagram. It says determine whether a quadrilateral is a parallelogram. Justify your answer using the slope formula. Well, instead of using any of those 5 that we just talked about, what I can do instead is I can use my knowledge of parallel lines. Parallel lines have the same slope. All right, the slopes are equal. The rise over run is equal. So I know the slope here is 1, 2, 3, 4, 5, 6 over 1. So I know the slope here is 6. I know the slope here is 1, 2, 3, 4, 5, 6 over 1 is 6. And I know the slope here is rise 1, 1, 2, 3, 4, 5, 6. The slope is 1/6, and here 1, and then 1, 2, 3, 4, 5, 6. I'm just counting the rise over run. The slope is 1/6. So if the slope of these 2 segments is the same and the slope of these 2 segments is the same, each pair of those segments must be parallel. So I know that Kn must be parallel to Lm because their slopes are the same. I also know that Nm must be parallel to Kl because the slopes are the same. That's only one way you could do it. There's also other ways using those different ways to prove it. We could show that this side is congruent to this side and this side is congruent to this side. We could even draw diagonals in and show that this length and this length are the same as well as this length and this length. Okay, we could just show that using the slope formula that these are parallel, and I could find the distance here and show that they're congruent. So any of those theorems that we learned, there's a lot of different ways to do it. I personally believe that just showing that both lines are parallel by looking at the slope is the easiest way, but you have opportunity to do it any way that you'd like, as long as you show one of these things, then you know for sure it is a parallelogram. Okay, so that's it for today.